Ja, also Beziehungssystems. Familien auch Systems.
So, welcome everyone to today's seminar. Today it's a pleasure to introduce Suresh Parekh, who is our PhD student here, who's going to be talking about his first year project. Suresh, the floor is yours when you're ready.
Okay, thank you very much. And hello everyone. I hope you all already know me. Firstly, firstly starting to give a little background about my research history. So I did my masters from IUCA Pune in Pune University in India. So I was working with high energy astrophysics, with X-rays and AGNs and trying to detect emissions in AGN. Then I moved to radio astronomy to again detect some reionization of the particles in middle of the galaxy cluster. So that was like working a little project. Then I moved to a little bit of cosmology, working with modified heat of gravity models, designing a pipeline for that. And now I'm working in infrared astrophysics. That is like the extragalactic. So I was pretty new to this topic, and I have no idea about when I arrived. I have no idea about what stellar populations are, what is starlight, which I've been using. So I have to go through the whole process of knowing that, and then our end goal is to design a code which is better than the current existing codes for stellar populations. So I have to understand the basics of that. So I have gone through all the literature and wanted to share that what all I learned and what are the missing pieces in the current existing stellar population theory. So let's try to figure out. So I will name it stellar population 1-on-1 or a short course on that. So please bear me for 40 minutes. So what is stellar population? The very first question. So it is like a bridge between stellar astrophysics and galaxy evolution. So we can try to infer many parameters of our stellar systems like galaxies or cluster using the information from stellar astrophysics. We can find ages, we can find the chemical composition if we understand the stars in the local universe and implant it on unresolved properties. So the first thing when it comes into stellar evolution is the HR diagram. It's a very ancient diagram which we work. The modern version which we are using is the CMD, the color measuring diagram. And we all know the different phases of the HR diagram. It is the luminosity or the temperature diagram, main sequence for the hydrogen burning, the red giant branch where there is hydrogen burning in the shell, where the center is a helium inert core, and horizontal branch asymptotic. I won't be getting into that details because you already know about that and more about the white dwarfs and then supernovae and all. But what important here is the mass dependent timelines. The star in whatever phase it is total timeline. It depends on its initial mass. So, for example, if we take if the initial mass is like around 10 giga years, then the lifespan is around 10 giga years. Then the life is 10 years, then mass it will be around one solar mass is or 10 one solar mass but get initial star has a 10 giga years lifetime. But it can be opposite. If the lifespan is around like 10 mega years or 20 mega years, then the solar mass will be like 10 solar masses compared to the previous one. And one more important fact is on the main sequence, if we go, the borderline is 0.9 solar masses. If the initial mass is lower than then, his lifespan will be greater than the age of universe, so which is not possible. Now, what is simple stellar population? That's all the range is going on about. So, in very layman terms, we can to define stellar populations, we take a package of gas and we collapse it to form instantaneously form the stars. And in that process, we study the whole evolution of each and every star, and also we can predict the chemical composition of the final stars based on the chemical composition of the gas and how it's been fragmented and all. And if we track the evolution process, we can find out the age of that particular star at a particular time. That's what we're trying to do in the stellar populations. But yeah, we all know it's more complicated than that. So we have tracks, we have isochrones. Tracks are like the evolutionary phase of each single star. Isochrone is like for a bunch of stars. In tracks, the parameters we have is effective temperature, luminosity, we have like the surface gravity. And in isochrones also, we have the same parameters for a bunch of stars with different masses, but at the same particular time. which follow single isochrone. And the isochrone can be defined as the bunch of mass which follow like the same evolution process for a single SSP. Like all the stars in a single stellar simple stellar population are on the same isochrone of a symbol age. That is, we can say that isochrone is like for 10 billion years, then all the stars in that particular SSP from that cloud should be lying on that isochrone. Now, initial mass function, I always have trouble understanding this because we are trying to understand how the gas is being fragmented and from the stars. So, what the question we are asking is, how is the gas distributed among the stars of different masses? To predict from first principles, need to understand fragmentation of gas clouds, which is a very complicated topic because we need to understand turbulence, self-gravity, magnetic fields, radiation feedback. So, it's very complicated for me to understand. So in layman terms, what we are trying to understand is how many stars are formed from a unit mass, or we can say how many stars are expected at a point on the isochrone. So here we can show the two very well used IMF, that is the Salpeter IMF and the Kroupa IMF, and that's how they have been looking. I don't know in detail about the IMF, so I won't be going in there. Now talking about the resolved stellar population. Like in the local universe or the Milky Way galaxy, we can identify or resolve each and every individual star and do the analysis for that. But when we talk about unresolved, we just have the light. So we have to study this particular area in deep and understand the stellar evolution and try to apply it for the unresolved part. So this is like a globular cluster for NGC 6397. And what we do is we create a CMD for that. And we have the white dwarfs, we have the main sequence for that. And what we want to do is we want to fit an isochrone so that we can infer the properties like age, metallicity, we can have the colors, etc. Before that, like we have two types of clusters. There is an open cluster, we only have hundreds to thousands of stars using main sequence dominant, and then in globular cluster, which is depopulated main sequence strong. It is thousands to 100,000 stars. But now, theoretical isochrone fitting is like the key for resolved stellar population analysis. What we are trying to do is we fit a theoretical isochrone based on the models, and what we want to infer is convert the physical parameters, like the effective temperature, the surface gravity, and the luminosity into colors. So what we do, we fit isochrone, and also along with that, if we have a very good populated color magnitude diagram like this, then we can infer the distance, metallicity, age, and reddening for our like globular cluster or the source. But if it is not like well populated or have lower sources, then there might be some like errors while measuring the air, or it won't be accurate. So we need a well populated CMD for that. Now again, only a single isochrone is not possible because even any population has multiple ages or multiple metallicities. So we have to plot like fit more than one isochrones. In here is shown Salary's isochrone of 3 different ages. So we have multiple ages, and it gets even more complicated for extended star formation histories, or even if you have intermediate age clusters. So we have to fit more isochrone. Not just for age, but if you see for NGC 5128, we have multiple metallicities. Here is like the histogram for the distribution of metallicities for the outer halo of NGC 5128. So it is complicated. How to do that? So we take we have to divide them into different age bands first, and then try to fit the metallicity for that particular age band separately. Now, this is like one of the approach that is being used. In here, as you can see, we have divided a diagram with different age bands, and then we fit the metallicity in there for better way. Now coming to the main part, it is the unresolved populations. In here, the things are complicated because we can't resolve a particular individual star. We just have the light. Now, how to study that? It is easy when it is individual. So, but we can't ignore this because we have very less bunch of galaxies in our local universe, which is not useful to understand the whole universe. So we need to study this. But for that, we need to resolve it. And we go for a reverse approach. We start to build a galaxy from the stars. So in the earlier, what it was being done is they try to fit the individual spectra of stars to match with the galaxy. But it was not so accurate, and it was also accurate for doing that. We can say like galaxy is made of stars, and we have resolved stars from Milky Way or from the solar neighborhood. So we take the stars and we try to fit it with the spectra of the Milky Way and then try to infer the properties. Or is there another result is we can compute the spectra of the star from the first principles. But the better approach, which is like the modern approach, what we are using is to create a SSP. The key ingredients of SSP is using IMF, isochrones, and the stellar spectra. Spectra. We know what is IMF, we know what is isochrone. So what we do is we create a simple stellar population spectra. Either we can combine the spectra and create a composite stellar population, or introduce dust in that if that is necessary. And how it works? We have to solve this equation. The S lambda part is from the stellar spectra, which was already been done earlier as well. But what we are introducing is we have to the stellar spectra is like the S lambda is a point on the isochrone, which is affected by the effective temperature, the luminous like the surface gravity, and the chemical composition, that is the that is the metallicity, and it has to be weighted by the IMF of whatever selected IMF we have, and then we sum it up all and create like a stellar spectra. This is like one of the SSPs. It is how we created with this method. Another method is fuel consumption theorem, which is being used for the Marston models. So we can using this we can create like a spectra, or we can create the band pass colors. We have this because measuring the colors is cheaper than measuring the spectrum. And this is how it looks like when we vary the spectra and the band passes with the ages. This is how it varies with the ages. Now, there is age metal. We have obtained like age metallicity discrepancy in optical. Why it arises is both age and metallicity reddens the whole population. This is why with a single color, we can't distinguish between an older and a metal poor and a younger and a metal rich population. We need to have more than one colors for that, which can be seen in this particular plot as well. Like for a single age and the metallicities, we can have two different type of populations. So it is hard to distinguish. It is even shown by Marisol in her 2005 paper. Like if you make a plot for both the colors, then the 3 giga for 2 solar masses and 15 giga for 0.5 solar metallicity, we can't distinguish between them. So can it be solved by infrared? Yes. Why? Because in infrared, mainly the luminosity is dominated from the RGB phase. It is highly dependent. RGB phase is highly sensitive and dependent on the metallicity, and also we have less contribution from the main sequence or the turnoff, which is like affected by the ages. So in here we have a higher gap between for the metallicity. If you get a JK band, and here as you can see, when you have a JK to BV plot, we can easily distinguish between a metal rich and the metal poor stellar source. Now we have just SSP libraries which are talking about. There can be two types. One is empirical, or there can be a theoretical library. So what in empirical we do is we take the spectra and we create the way how I just discussed. For example, the Mealy's, Tulip, and all the way I have shown in here. Mealy's is like a very popular library with around 985 stellar sources. But here the problem is we don't have a larger variety of the parameters, because in here, as you can see the problem, if we go to the local universe or it's in the solar neighborhood, the mainly the stars which we have are they're not like already metal rich, so we can go to like a higher temperature for like that particular part remains empty. So there is a lack of all the parameter space in theoretic in empirical libraries. And when we go to theoretical spectral libraries, so in here, yeah, we can compute a spectra with the like first principles and the models. Okay, we can have a very high resolution spectra where which can be which is like a challenge in the observation, because in the empirical libraries we need to have very high resolution spectra. It has to be like flux calibrated. It has to be very well calibrated, and then only we can have a very good SSP population with a high resolution. But in here we are computing it, the star in our computer, so we can have a very high resolution. But the problem is it is harder to compute atomic and molecular lines. So it gets difficult to compute all the possible computer lines. So that is where the theoretical spectral lies. And already we don't know all the known physics, so we can't try to implement or make the exact replica of a star. Now for full spectrum fitting, what we do is we take this the model and we try to fit it with our observed spectra. And when we do, we measure residual, we measure the chi-square, basically mainly all the pipelines which I will discuss later, work on the chi-square minimization technique. And then we using that, we can infer the age, metallicities, and other abundances parameters from that. Now in our analysis, we are using 6 different models. There is a Millis, Marrowstone, XSL, the CO3, CO9 pipe of star. So here I will like shown how the differences, how they're different from one another with 6 properties: type, size, library, resolution, speciality. So Millis is like one of the benchmarks which we have been using, which is very good for infrared analysis as well. Marrowstone has strong TPAGB transition, uses C2H2 for higher rates of dating. XSS is a very high resolution stellar bomb. It is a resolution of around 10,000. It is very good, but separate static variable giants advance near infrared fidelity. BCO3 is like a standard model or a benchmark for the optical part. Stochastic AGB treatment, the standard optical benchmark. Then we have conjoint models. One of the good thing about the conjoint models in their paper they have mentioned, we can assume like the error bars for the mass and the ages to be like around 3 decks, but they don't provide error bars for the spectra. So parameterized AGB defines error bars for mass and age. Okay, and pipe of star is a total theoretical model. So it is very highly high resolution, 5,000, 50,000 is the resolution of pipe of star. New atmosphere targets dwarfs, galaxies at a metallicity of 0.0001. Then what we're doing is we already had like 21 spectra of 21 globular clusters of NGC 5128 from the Denman Hunt et al. 2024 paper. And in April 2025, we observed 10 more GCs from the halo of the NGC 5128. If you can see the table, so plot in here, the blue ones are the which were observed in 2025 April. And the Thais was the PI, there was Louis, there's Anna, there's Rogero, except for the dog. And we use the solar telescope for that. And you can see this all 31 spectra in here. Few we have very good SNR, few we have a lot of noise, so we have to manage with that. And what we did is SSP fitting with Starlight. We use the 6 different all the models. We fitted the spectra, so the residual, and create the bar plots for the age, and also infer the metallicities in there. Can't be good very well in here, but yeah, we have like average age, average metallicity, chi-square, and ADEV. All the models are performing differently, and we need to compare how they are related to each other for inferring ages and the metallicities. So here I plot like a corner plot for the age and for comparing the ages and the metallicities between the different models. Ideally, they should all lie in the middle diagonal line, but no, it can be seen there is correlation, very well correlation between for the metallicities, but for the ages, okay, there is something weird going on. And here, like there is comparison of MGFE, the metallicity research for the optical versus the metallicity on the x-axis. Here too, we try to observe like a linear trend, but no, it is not visible. But we are going through why the problem, we don't know right now, but we have to figure that out. In here, we have like the edge split, that is like the age tracer from the optical, and the ages obtained are on the x-axis. If the edge beta is in the increasing order, what should we expect is the bar should be like in the should be arranged in increasing order, but it feels like it is arranged randomly. So still, we don't know why there is like age discrepancy between the optical and the NIR part. And one more analysis, what we tried is to combine all the 31 spectra, so we can have a high resolution spectra with a higher, better SNR. So for this spectra, the SNR which we got was around 300, And yeah, we were able to fit the pot, do the fit. And in here, what we expect is there should be multiple edges, there should be multiple metallicity, and yeah, we do infer that, and the fits are good for this. So in conclusion, from this analysis, what we want to try to conclude is, okay, the models are not perfect, nor is our pipeline. So what we need to do is, the single best paradigm is insufficient. Using a single model for our analysis, because the outputs are model dependent. So future work requires multi-model approaches to fully account for model dependent uncertainty. So unless and until the models are not fixed or our patterns are not well improved, this is what we have to follow. We have to go for a multi-model approach. And to continue this forward, what we had like a sole proposal accepted in the December, in the October, I guess. So we wanted both the optical and the near infrared counterpart for the same data. So we can check the age metallicity discrepancy which you observed from the both optical and NIR for at the same time. And also, what more we are trying to do is to improve the code. What we say is, we don't have error bars on the model side. We want to try to fit the error bar with the observed spectra as well. But it is insufficient for the models for the codes which we have right now. Because all the codes depend on the chi-square minimization technique. In chi-square, we can include error bars from the model side. So we need to have a new statistics using which we can try to implement the error bars from both the model as well as the observation side of the observed spectra. So we propose brain. Not mine, but our brain. So we are trying to develop this code, me, Rogerio, and Rafael. So the name brain comes from, there are two reasons for the name brain. One is Brazil, India, or the second one is from Pinky and Brain. Whatever you like, you can take the assumption. Now we are comparing the 4 widely used stellar population fitting libraries: Starlight, PPXF, Fado, and Firefly. As I said, all the 4 have mainly works on chi-square minimization. Starlight is like the robust benchmark. It is one of the widely used also library. PPXF is good for kinematics and stability, also very good for optical as well. Fado is good for stellar formation physics. Firefly is just independence, it's a specialty of that. But we can't try to fit error bars from the theoretical models with the observed spectra. So that is like the main goal which you want to try to achieve with brain. But that is not the main goal. Okay, we want to add error bars from the theoretical side as well for the fitting. We want to make it very fast. Currently, like if I want to do this analysis, I am running like around 3100 spectras, because for 31 sources I have simulated 99 more spectras to be like correct statistically. I need around 4 days to run all the 6 models on that. That's a lot of time. And if you talk about for data cube, then okay, it will gonna take a lot of time for that. And if you have a very large survey coming from JWST, then it will take years or like decades to analyze the whole thing. So we need a faster code which we can do it very fast. And also, like if I go to conference, someone is presenting something and the data is available like openly, I want to check if it's correct or not. So I need a tool that I can do it quickly. So it has to be fast. Easy to use is like the main point, because for doing this analysis, I had to extract all the single SSPs, the 6 SSP. It was a very big headache. I need at least 1 month to do that. Each and every SSP is a different method to extract them or to construct them. So if you want to do a quick survey or quick like a look for quick and run for that, it's got a very big hazard. You already need your system, you need to open it, you have to go to that. But if you want to do it right now, I want to, okay, you give me a spectra, it can be done. So it has to be easy to use, ready to use. And yeah, we have a very handsome guy working like making revolutions in the GPU. So we have to make use of that. It will be the GPU based pipeline. So we can simulate as many changes as we want and make it very fast. But yeah, we will also have like a CPU based pipeline as well. So don't worry. And yeah, we will be making like a web-based platform that from anytime, anywhere, you can run it. Like you are in a conference, you don't have your system in there. You can take your phone, download and upload it on the website and get your fix. I'm not trying to sell like a marketing person, but yeah, there's some plan. So we want to develop a web portal which can be done on that. So ready to use. So basically, that is what brain we are working on. So this is like the whole PhD project which I have been working on, and thank you very much. If you have any questions, then I'm welcome.
You had 15 more minutes.
Okay, we can.
Questions for
Yes.
Suresh?
Go back to the rabbit theoretical models.
Yeah, coeval. That one.
Here.
Yeah. The first one, are those measured lines or just noise?
I have no idea.
Theoretical.
I have not gone in detail. These are atomic lines, but I'm not sure.
No, it's the full range of atomic lines.
Yeah, it is like a whole range of atomic lines in there. That was I was trying to argue. We can't like compute each and every lines.
Yeah, but what kind of resolution do you need to catch those lines? No.
Or more than that, because pipe of star is 50,000, at
Yeah.
least we need better than that.
Question? I have one.
Yeah.
I have. Go ahead.
So what about the discrepancies with the GCs that you just showed?
Yeah.
Can you go again, and maybe I was too fast? Those.
Yeah.
So what do you think might be happening there? And why XSL,
Yeah.
X
X shooter.
shooter? Well, they're
definitely-
pretty similar.
X
Yeah.
shooter is actually giving a good trend. It should be increasing linear, but it is very less. But if you see in the other models, it is not there.
Can you explain a bit more the indices with like slowly? What are they? Because
Okay.
MGFE, or is it the MG
It's
over
actually-
FE? What it is?
No, it's just MGFE. Here we have the mean metallicities for each source, and the colors are indicated from this gradient for the mean age. I just made this plot yesterday, so I don't know. We haven't tried discussed about that much.
I can give a little bit more
Yes.
details. Like in GFE prime, it's a metallicity indicator removing the effect of alpha enhancement. And since we are measuring the metallicity on the X axis from the near infrared spectrum, the other one is coming from the optical. If we would have a good agreement, we should see like 45 degrees correlation. We are not seeing that. This means that the models, they are failing. And like if you go to the next plot, this one, this is not H in this case because of figure run, remember?
No.
This is a metallicity problem actually that is happening, like we are seeing sort of a go to figure one of the paper. This one. Look, they are all old because they lie below the maximum age beside one source that lies very on the top. And what is making this sort of gradient that we are seeing here is actually metallicity and not age. So that is why we were expecting finding like this correlation there with metallicity, and not the like the other part. This we need to remove from the paper.
Okay.
Okay, this is not true.
Didn't get, but mean metallicity.
The metallicity should be a 45 correlation.
So these other indexes, it's only one index.
It's one index
One index
from the optical,
from the optical, and the mean metallicity is from
from the
others.
near infrared, fitted from the near infrared,
Oh, near infrared and
from the
optical.
same GC.
And the mean metallicity from both the fitting.
Mhm.
So because here we are indices and spectral fitting. Did you-
Indices are from the Mike Beasley's paper.
Yeah.
I have taken from there, and the metallicity is what we got from our fitting.
But yeah,
We should do
We
this in the optical.
We
but
need-
we
do
don't
not
have the optical counterpart
of
this.
Spectra to do that.
Okay.
That
so
is-
we need a solar attack, we need optical spectra.
Yeah. That's what we will be doing, like in our
Yeah.
like a dwarf regime, to have both counterpart and check.
But my question is, what is the difference between fuel consumption theorem and isochron model?
I don't know fuel consumption theory. That's why I try to say I couldn't understand. Yeah, I'm so sorry for that.
So this is for the next seminar, okay?
next end of the next semester.
Yeah,
Probably if we have the brain running.
yeah.
Another question, the same time. If you compare the same index with different base, are there any correlation or no? The same index, but in two different marathon beings, CO.
Yeah, okay, it's here.
No.
So you can see.
This is metallicity.
Yeah,
Since
we don't
this
have it.
agrees, but no, but since metallicity more or less agrees, then it should agree there, like,
Marathon has a
yeah, yeah,
And the age
is the
doesn't
other one.
agree so much.
No,
The red.
It is more or less agreement.
yeah, like we took model against model to see if we see some trend in something, but there is also like the difference between the resolution of the models, the spectral resolution. We are degrading the data, but like it's a little bit different doing the fix.
that should affect metallicity, not age.
Yeah, much more than.
Basílio?
So let's say if I understand what you did here, you have 6 models. Which you listed in the previous table. So do they all, each one of them has a base, a spectral base, which are all simple stellar population.
Yes.
Spectra.
Yes.
There are some information there that could be useful. Is the IMF on which they are based the same?
Yeah, we have used.
They're all the same.
We have used the same IMF for all of them.
So I wonder if, for instance, the discrepancy in age that you see, if you want, and you've run the same spectral fitting codes
Yeah,
to all of them. The
Yes,
results
yes.
show, what is that, starlight?
yeah,
So you've run the starlight on each of these
yes,
models, and the comparisons you made are based on starlight alone.
yes.
But now you're trying to go an extra step in using different spectral fitting codes.
Mhm.
So this will just add
Não.
A layer.
to the discrepancies, if I understand. Wouldn't it be easier first to understand where the discrepancies are on a single spectral fitting code? How you can explain the different models?
Mhm.
And I think that it could be that the understanding why, for instance, the ages disagree so much. The answer could be in the bases, in the SSP bases themselves.
So we,
Investigating
there's something,
that.
Yeah, it has two phases. The first phase is to understand this. The models, they are different. That we know. They are introducing lots of differences. And for instance, if you want to know the mass of a galaxy, it can be highly affected on the models you are using. That is why when you do a comparison of a sample, you should always fit them with the same way of doing, okay, to be able to do the comparison. But the next step we want to do is like, okay, the models, they do not provide error bars. They should provide error bars because there is so many things that go under the carpet that they should provide it. And there is so far no fitting code that is able to include errors on the model side. And that is why we want to write a new code. We don't want to fit those same data with other codes. This has been done a lot. People have done this. And the results, they are nearly similar if you choose one code or the other. What makes the results change is using different bases. That is the point. And this has never been done for the near infrared. And then Anna is leading a project to observe GCs, extragalactic GCs in the near infrared taking this spectrum. And what we are trying to do now is to fit with all the available models to see. We are not going to say which one is better than nothing, just to show the difference between them and how discrepant they are. Like you can derive a young age for a GC that has a very tiny each beta index, and this is not true. It should be an old GC from that side, okay? And that is what we want to show with this project.
Yeah, this is all fine for me. I just wonder if looking at the SSP basis is a nice approach towards understanding why the different models are leading to discrepant results.
This has been
Look at the
done a lot.
basis
Yeah.
and compare them. So what is Z metallicity tau age on this Miles
Miles.
is it called model, and look at the same age and metallicity. What is the
It is-
basis
has been done.
spectrum
Yeah,
for the BC003?
It is
How
done.
do they compare?
It is done in every single paper where they present new models. Every single paper has this.
And they have to differ somehow, otherwise the
Yeah, for
results,
sure.
the results running starlight shouldn't differ.
I say this is like shampoo for shoulders. If you have lots of versions, it's because no one works. Okay, that is the same here. We have lots of versions, no one is working properly. That is the point.
Okay, are there any more questions? I have one suggestion that occurred to me. There are some studies looking already at the possibilities of seeing some signatures of multiple stellar populations, and maybe it's just another source of error, but we should take that into account.
And we have to take that.
And it has been done for the optical, not for the near infrared, so we can have a check on that. And the last one, is it because
No, because, yeah, it's related because this would just broaden a little bit the age variance, not that much multiple
Yeah.
populations, so.
And last but not least, when is brain gonna be working?
Only for Christmas.
No, not Christmas. Probably by the end of next
year,
semester.
Next
Yeah.
year, Christmas.
Okay, in the next
It-
short talks,
won't-
we're gonna have
No, not
a
short
brain
talks.
tutorial.
Like next like end of semester like talk we can have, not the website, but we can have the code ready by then.
So we can have tutorials.
Yeah.
Yeah, of course.
Oh, I have no question about your promise.
It's like Jensen.
Because you want to deliver uncertainty quantification at the same time you want to be fast. We somehow are antagonistic. because
Yeah.
If I mean, the basic stuff like MSMC doesn't work, it's not scalable and so on. So what's your plan? What's the first challenge that you need to solve?
So basically that can be solved not with the code, but when we try to build a website, because what we can do is we can train a model based on all, like we can take the whole SCSS down, run our code on that. It will take some time, but we can train the model based on that and try to create a model spectrum for the observed spectra. And then what we can encounter is if we take the residual and see if there is something fishy, and only then there will be a flag raised. Then the actual code will start to run. And in that, using this approach, we can make it quick, very fast. That was the approach which I was thinking about.
But there is still the uncertainty quantification part. and
Yeah,
stuff.
that we have to discuss.
Okay.
Okay, if there are no more questions, let's thank Suresh again.
Yeah.
Note the speakers from the semesters, and then we're done. Happy holidays.
Just next week.
See you in March.